I have created a PDF regarding group theory and in particular the Lie algebra of 3D rotations. So we are talking about SO3, the special orthogonal group in 3 dimensions. So I want to show you some simple examples and also a script, a MATLAB script that we will run to illustrate some examples. So in a 3 dimensional space, rotations are represented by orthogonal matrices with a determinant +1. In particular, the transpose of the matrix that we call R applied to the matrix R is equal to the identity, and the determinant of R is equal to 1. In particular, just to give you some more perspective on why the determinant is chosen equal to 1, is that if we consider, for example, the determinant of R transpose R, that's equal to the determinant of R squared, because the determinant of the transpose is equal to the determinant of the matrix itself. So the determinant of a matrix squared must be equal to 1, because that's the determinant of the identity. And determinant squared equal to 1 means that we can choose either determinant equal to plus or -1. If we fix the determinant equal to +1, then we are going to fix the direction, let's say, of the rotation of a certain vector. So I don't want to get into this detail, but of course, if you think about it, you can rotate a vector around a certain axis, clockwise or anti-clockwise, and this is why you have this kind of choice in the sign of the determinant. Then the set of these matrices R is the special orthogonal group in 3 dimensions, SO3, and we can give, of course, 3 different rotations to be able to describe all possible rotations. So, for example, we have a rotation around the x-axis, a rotation around the y-axis, and the rotation around the z-axis. They can be written in this form, so I will not go into these details here. It's quite intuitive that, for example, a rotation around x can be written in this form, because this one here in the first row and first column, and with these zeros here on the first row and first columns, this simply means that we are going to leave the first component of the vector that we are going to rotate unaffected, which means that we are not going to change the x component of a vector. We are just going to change the y and z component of that vector, because we are going to rotate it around the x-axis. So it is quite intuitive. I will show you the implementation in MATLAB of this. So we are going to give some kind of proofs to this without writing down or drawing some examples on paper. So for now, you take these matrices for granted, and I will go here to this section that I have prepared to denote the fact that if we consider infinitesimal rotations, for small angles, theta, which can be theta x, theta y, or theta z, the rotation matrix can be expanded in this form. So we have the identity plus the angle times some kind of matrix, which can be, so here it is denoted as L, and if we are in the x direction, we will have Lx. If we are in the y direction, we have Ly, and so on. So also in the z direction, we have Lz. L is called the generator. This is a very important matrix in this case, because it generates a rotation, an infinitesimal rotation, and it is an element of the so-called Lie algebra. And we will see what the Lie algebra is. This is something that will also appear in quantum physics, and also when we consider other types of groups, like the Lorentz group, the Poincaré group, and that's also related to the theory of angular momentum. But anyway, here in this case, for example, if we consider the x direction, so we can expand this matrix in terms of powers of theta x. It's like considering a Taylor series. You expand the matrix, so you have to rewrite this matrix as the identity plus the angle that can be factored out times another matrix. So, for example, the sign of theta x can be written as theta x. When theta x is very small, we are going to truncate the series to first power. And similarly, the cosine can be written as 1 minus, and then you have terms which are proportional to theta squared. So you don't have, so when you expand the cosine, you don't have a term proportional to theta, you just have a term proportional to theta squared. So you have the first term, which is 1, and then you have something which is proportional to theta squared if you expand the cosine in a series. And we are going to truncate the sum to first order, so the second order terms do not have to be taken into account. So you don't have to take them into account. And when you do the algebra, which is very simple, you get the identity plus theta times some matrix L. And in the case of the x-axis, it can be written like this. So it's this matrix here. Similarly, you have the one on the y-axis and the one related to the z-axis, and so on. So L is called the generator. You have three generators along x, y, and z. And in general, the Li matrix is antisymmetric, as you can see. And these matrices together form the so-called Lie algebra little SO3. It is denoted like this. The Lie algebra considers the commutator. In particular, the commutator between two matrices can be written like this. The commutator between Li and Lj is written as Li Lj minus Lj Li. And the results that we will show in MATLAB are the following. So if you take the commutator between Lx and Ly, it will give you the generator along Z, and then you have cyclic permutations of that. So the commutator between Ly and Lz will give you Lx, and the commutator between Lz and Lx will give you Ly. So these are the commutation relations of the algebra, which are identical to the vector cross product structure. So you can also write that as some kind of cross product in this notation. And this is equivalent to the angular momentum operators in quantum mechanics. So in quantum mechanics, for example, if we call the angular momentum operator Jx, we have the commutator between Jx and Jy equal to I h bar Jz plus cyclic permutations of that. Now, there is also a connection with the exponential map. In particular, the Lie algebra elements generate finite rotations. So when we talk about the generators, we are talking about infinitesimal rotations. But by using the generators, we can also create finite rotations through the matrix exponential. And I want to show you that in MATLAB as well. So in particular, we have a rotation that depends on an angle theta and an axis of rotation n. So this n here is a unit vector, which is the direction of the rotation. So we are going to rotate a vector along this axis. It can be the x, the y, the z axis, but it can also be a generic axis, a different type of axis. And we have an exponential of theta times this ln here, which is if you want to think of this in a certain manner, you can think of this ln as the vector, the generator vector along the n-axis. So in particular, it is the dot product between a vector given by Lx, Ly, and Lz with the unit vector n. So it is nx, Lx plus ny, Ly plus nz, Lz. So in particular, this is an exponential map that links the Lie algebra to the Lie group. So in particular, when we talk about the Lie group, we are talking about finite characteristics, let's say, so global characteristics. We are going from the infinitesimal to the finite domain. So little SO3, then we take the exponential, and we have a map that maps this little SO3 to the special orthogonal group in three dimensions. Now, the physical intuition is that the matrices Lx, Ly, Lz are infinitesimal rotation generators, and each of them represents a small displacement around the coordinate axis, a small rotation around a coordinate axis. And combining infinitely many infinitesimal rotations gives a finite one through this exponential map. So why are those infinitely many infinitesimal rotations? It's due to the fact that the exponential can be written as a limit of a certain power of matrices. Now, I'm not going to write that, but you have a limit as some integer goes to infinity, and therefore you can think of this as an infinite amount of products, an infinite amount of products of matrices, and that's why you can think of that as applying infinitesimal rotations an infinite amount of times. So that's some intuition without being rigorous here. And the same structure governs the spin operators in quantum mechanics, of course. So here I have also prepared a summary table where SO3 is a mathematical object. In particular, it's a group. And then we have this simple description. So it is the set of all finite. So the important word here is finite 3D rotations. And in a similar manner, the generators form the Lie algebra, and they can be thought of as infinitesimal rotations. And it's denoted, so they are denoted as little SO3. The generators are Lx, Ly, and Lz, so they are antisymmetric matrices, which are called generators. And then you have an important concept, which is the commutator, which defines the algebra structure. So it is the algebra because this is some kind of algebraic property. You have a product of matrices, and then you have subtractions, and that's equal to basically another matrix, which is still a generator. So that's the algebra of a group. You also have an exponential map, which connects the algebra to the group. So these are properties that repeat themselves when you consider quantum physics as well. So they are the fundamentals, the fundamental properties of groups that are found in quantum physics as well. So it's important to understand to start playing, let's say, with this kind of properties. Now, I've also prepared a script. This is a live script in MATLAB where basically I define here the matrix Rx that you can see here. I define the infinitesimal generator along X, which I call the drx. In particular, the generator is this matrix divided by divided by theta x. So we get Lx here. And by the way, this drx basically can be derived by taking the expansion of this Rx, and that will give you the identity plus drx. And that's very simple because the cosines will give you 1. So you have the identity plus, and then you have a bunch of zeros, and then you are left with the sines, the sinusoids, and the sinusoids will give you this theta x. So because the sine in the limit where theta x is very small, you get minus theta x for minus sine theta x, and of course you get theta x for sine of theta x. So when you divide that by theta x, you get the generator along x. And similarly, I have defined the matrix Ry and also the generator Ly that you can derive from dry as well. And similarly, I do the same thing along Z. So I have the generator along Z. And here I also calculate the commutator between Lx, Ly, the commutator between Ly, Lz, and the commutator between Lz and Lx. And what I get is, for example, the commutator between Lx and Ly gives me exactly Lz, if you think about it. So if you check, this result here is equal to Lz, and then the commutator between Ly and Lz gives me exactly Lx, if you check, and so on. So you get the commutator between Lz and Lx is equal to Ly. as you can see from these calculations. And then here I also decided to add this section on the exponential map, which is basically some kind of verification. So I have defined the vector along y here, and then I have written a matrix R, which is the exponential. So in MATLAB here we have the exponential of a matrix, which is exp m, which is given by basically you have a certain angle. So I can define it as theta x times Lx times the first component of n, and then I have plus theta y times Ly times n2 plus theta z times Lz times n3. And since here I'm considering n as the y-axis, if we do this calculation, we must obtain the rotation matrix along the y-axis. And if you do the calculation, so I have already done the calculation, this is the result, which is exactly this matrix here. It's Ry, which is the rotation along the y-axis. And then I've also prepared another section here, where basically I consider an initial vector, which is given by the components 0, 0, y. So it is a vector that you can see in blue here in this plot. I have decided to draw it not at the origin, because otherwise it would overlap with the axis. I have decided to plot it slightly off the origin, but it's close to the origin, but never mind. So you can see the vector in blue, and then you can see the three axes, the x-axis, which is this brown arrow. Then you have the y-axis, which is this cyan arrow, and then you have the green arrow, which represents the z-axis. Then we rotate the vector along. So I have decided to rotate the vector along the y-axis by defining this vector 0, 1, 0. So you can either define the rotation matrix by using these three matrices here. So here we are rotating around the y-axis, so you can choose basically Ry, but I have decided to define it like this with this exponential map, because you can be more general. In this case, you can rotate around different axes by changing a smaller number of parameters, so it's more convenient. And you can see that the rotated vector is simply this red arrow. So when you rotate around the y-axis with the right-hand rule, you can basically obtain this red vector, and this is exactly what we get by using the exponential map. So you can also try to play with this script and try to rotate around more generic directions if you want. This was just a simple example to show you some important concepts, in this case related to SO3, the special orthogonal group in three directions. In quantum physics, we have, for example, the special unitary group in two dimensions, which is still related to SO3, and we will see more about that in future videos. And we'll also have to deal with some important algebras, which are fundamental in physics, like the Lorentz algebra, which is some kind of generalization of this. So in this case, we are rotating vectors in three dimensions. When it comes to the Lorentz algebra, for example, we have four dimensions because we have space-time. So we have three dimensions of space and one dimension of time. And you can try to think of the Lorentz algebra as the algebra related to rotations, quote-unquote rotations, in four dimensions. So they are not exactly rotations like in this case, because in that example we have a different type of space. It's not Euclidean space. You have a Minkowski space where there are both rotations but also boosts, which are those operations which basically are not exactly rotations, even though they can be thought of as some special rotations, but you are considering two reference frames with a different relative velocity between them. So it's related to special relativity. But they can be still thought of as special rotations, and I will try to give you some more intuition about that. If you don't know about it, you will see some more material on that. And that's it for this video.